Hey there, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video to solve another mechanics problem. So let's get into it. So in this problem we have just a structural component, and all we're doing is calculating the moments of a given force about a point. So in this case we've got this force here acting over here. Doesn't really matter what it's acting on, could be anything. The important thing to know is the line of action of the force and the perpendicular distances from the point where we wanted to calculate moments about to the force. Now, in this particular problem, we've got this dimension here, 2 meters, and this dimension here, 5 meters, horizontal and vertical. So for this problem, the simplest solution is probably to break this force up into its components, horizontal and vertical. Right? And we're already given this 3-4-5 triangle here. So if you're familiar with using that 3-4-5 ratio triangle, then you probably already know that the horizontal component here is going to be 40 and the vertical one is going to be 30. No, it's not. It's going to be twice that. But anyway, we'll get to that as we go through the problem. Just redrawing the problem with our force applied there and using the principle of moments, also known as Varignon's theorem. Now, you should be referring to your textbook or your online resources. Your subject site might be on Canvas or Moodle or Blackboard or something like that. But anyway, this is what it looks like at UTS. So here we've got the chapter or the page on moment of a force, principle of moments. So in this page, which is in the week 1 module for UTS students, we've got this video here on moments of a force, which is a bit of a brief overview where we do go through, or where he does go through components. But if you want to see the full lecture on scalar formation and the principle of moments, you can go back to the week 0 module and look here. So if you're studying somewhere else other than UTS, then you'll have something like this, or if you don't have that, you can always, of course, go to the textbook. All right, so we get to the page in the textbook on principle of moments. So you may not have an online site with all your learning materials, but hopefully you'll have a textbook that you can look up and see the equations and information and so on. So all right, so in the textbook you can see here is how they've written their equation for Varignon's theorem, or the principle of moments. Right, so they've got it written as fxy minus fyx. Now, you need to be careful. This is not a general formula. This is only valid for their particular case. If we go back to my page here, you can see how I've written it. I've written it like this. So the moment is equal to the horizontal, or the x component, times the perpendicular distance from point O to that force. And in the front, I put plus or minus, because it depends on where the force is and which way it's going. Right? So it's not always going to be plus, or it's not always going to be negative. So just be a little bit careful with just using an equation without really knowing how it works. So this in the textbook is only valid for this particular case, whereas mine is more general. Now that we have this, let's find our components in the horizontal and vertical directions. So that's F equals 100, and let's define what X and Y are in this case. So we're defining X as horizontal and positive to the right, Y as vertical and positive upwards, and we're also defining anti-clockwise as positive for moments. So this is the strictly correct set of positive directions for X and Y in these directions. All right, so our horizontal component is this one down here, fx. And if we complete the little right-angled triangle here and use Pythagoras and trigonometry, from our ratio of triangles here, we get, using the ratio, 4/5 times 100 gives us the length of this side. Okay, so that's why we've got 4/5 times 100 here. If you're not sure about this, go to the trouble of using trigonometry to work out what these angles here. So you can use tan of 3/4, or a cos of 4/5, or sine of 3/5, inverse of those, to find the angle. And then our vertical component, over here, acting downwards, is the length of this side of the triangle. So using our ratio, 3/5 times 100 gives us that component. Note that I've drawn this component acting here through its proper line of action rather than over here. And I talk about this quite often in my video, so I won't go into it this time. All right, so we need the perpendicular distance. So when we're calculating the moment, it's important that we know the full definition of the moment, okay? And that is the moment is equal to the magnitude of the force times the perpendicular distance from the point where we're taking moments about to the line of action of the force, right? So here's the line of action of the force Fx. dy here is the perpendicular distance from point O to that line of action. And then similarly, we've got our line of action of the force Fy coming down here, and the perpendicular distance from point O to that line of action is this distance here, dx. Okay, so now that we have all that, we can put that into our equation that we had up here. So the moment is equal to Fx times dy. So 4/5 times 100 times 2. And now we need to consider, is it positive or negative? Right, so let's look at the force. So it's pushing across to the right here. So we can hopefully see that that's going to tend to rotate around that way. If you're not sure, just grab a pencil, something like this, and push on the direction of the force. Okay, I'm not sure if that's the right way or not for the problem. It's gone off my screen. So push or push to see whether it goes clockwise or anti-clockwise. Okay. Similarly, for when we do the vertical force, push down to see whether it goes clockwise or anti-clockwise. Okay. Or if it's from this side, push down to see whether that goes clockwise or anti-clockwise. And then look back at what you've defined here as positive or negative. Okay, so we've defined anti-clockwise as positive. So in this case here, we've got a clockwise moment caused by the Fx component. So that's going to be negative. All right, so let's look at the next one. So we have 3/5 times 100. So that's our component of the force in the vertical direction times its perpendicular distance, dx, which is 5, pushing down here. So that's also going to tend to rotate around that way, okay, which is clockwise. So that one is also negative. All right, so we're now done with that. Let's put in our numbers in our calculator and calculate the answer. So we get 460 Newton meters negative for the moment of the force about point O. And so therefore, because it's negative, that indicates that the moment is clockwise, which we've seen by inspection. Okay, so just something to note here. You may be tempted to think something along the lines of, if we've got Fx here is positive and dy here is positive, then shouldn't Fx times dy be positive? No, that would be a mistake. Right? What we need to do is not look at whether the force itself is positive or negative, but we need to look at the directions of rotation about the point for each force individually. Now, in 2D, we have to do this. We just got to look at each force in turn and work out whether it's causing a clockwise or anti-clockwise rotation. But if we know the vector form of the moment equation, then the vector, assuming you do your vector cross products properly, then the vector form of the equation looks after all that for you. That's the easiest. That was a long explanation of the easiest way to solve the problem, by finding the vertical and horizontal components. What we can also do, and I think I've asked my students at UTS to do this, is to solve the problem by finding the perpendicular distance to the line of action of the original force. Okay, so rather than finding components of the force, we're now going to try and work out the perpendicular distance. So I've redrawn the diagram here. extend the line of action of the force, and then draw the line perpendicular from the point about which we're calculating moments to the line of action of the force and perpendicular to that line of action. Okay, so we've now got to do a bit of geometry and trigonometry to work out the length of this line here, D. A number of ways of doing that. All right, so just putting down here first, though, the moment equation, and here I've just said, because I can see here this is going to be clockwise, I've just said, okay, the moment about point O is going to be clockwise. So we just need to work out D. All right, so if we draw this line here, this over here is a right angle triangle. So hopefully we can see that this distance here will be H sine theta. Okay, so we don't know what this angle here, theta, is yet. And if we label these two angles in here, so this angle here, alpha, which we don't know yet, and this angle here in here, phi, that we don't know yet, need to do some trigonometry. You can see that this angle here, theta, will be equal to alpha plus phi. All right, so let's first work out, so what we need to realize here is this angle here, alpha, is, I think these are called alternate angles, correct me if I'm wrong, but what I do know is that this angle here will be equal to this angle here. So from this right angle triangle that we've got down the bottom here, this is the opposite side, this is the adjacent side. So if we do inverse tan of 2 over 5, we'll get this angle. Okay, inverse tan or A10. So depending on where you've been to school, what you've done before, you may be familiar with seeing this as tan to the minus 1, 2 over 5 rather than A10. Either works. And the angle here, phi, from our 3, 4, 5 triangle. So again, opposite over adjacent, inverse tan gives us the angle phi. So we can calculate those angles. And from Pythagoras rule, from this triangle here, right angle triangle, so the length of this hypotenuse here, h, will be square root of 2 squared plus 5 squared. So putting all of that into an equation. All right, so we've got D equals H sine theta. So theta equals alpha plus phi. So we've just substitute that into there. And we've also seen that H is equal to square root of 2 squared plus 5 squared. So that's just substituting all of these, 1, 2, 3, 4 things into this equation here, and then into this one here. So 100 times D. So if we do our maths, we get 460 Newton meters as we obtained before. All right, that's the second way of solving the problem. So you can see it's a little bit more work to do with your trigonometry. All right, so the next one is to use the vector equation. So use the vector moment equation, R cross F. You should have studied cross products in, so people at UTS should have studied cross products in physical modelling and or math modelling 1. So now what we need to do is to put our force into vector form and also to work out this position vector R. If we define our position vector R from down here, point O, to the point where, so you can define R as anywhere along the line of action of the force. Okay, so you could put it here, you could put it up to here, it doesn't really matter, but we know these dimensions here, so it would make sense for us to define our position vector as going from point O here to the point here where we're showing the force being applied. Okay, so R equals 5i plus 2j. So you can see, if you know your vector notation, as you should, in the x direction, it's 5 times the unit vector I, plus in the y direction, 2 times the unit vector j in the y direction. Okay, so that's our position vector. Now for our force, magnitude is 100. In the horizontal direction, it's 4/5 times I, just using our ratio of triangles as we did before. And then in the y direction, it's going in the negative y direction. So 3/5 times the unit vector in the j direction, and we've got the minus sign out the front. Okay, and that's newtons. So we've now got our two vectors, r and f, position vector and the force vector. Now, with our vector moment equation, it's important the order that we do the cross product. Okay, so you should remember from your maths that the order in which you do the cross product affects the solution, right? So for the moment equation, you need to do position vector r cross product times the force vector. All right, so let's do that. R cross f. So we can take out the front here, the 100. Now there's a number of different ways of doing this, so you may have a favorite way from maths. I like to just multiply through. So I put the 100 for the magnitude of the force out the front, and then in square brackets, I'm just going to multiply through each of the components. So here I've got 5i times 4/5 I, and then you just do the cross product of the two unit vectors. Then the next one, we have 5i times 3/5 j. We've got a negative there, so I cross j. So now we're going to multiply through this one by 2j. Same thing again. So 2 times 4/5, and now we have j cross I, because we're multiplying this component by this one. And then next we have 2 times minus 3/5. So we've got that there, j cross j. So now hopefully you remember that cross product of two vectors going in the same direction will be 0. So I cross I is 0, and also j cross j will be 0. But before that, hopefully you know that I cross j is equal to k, and then j cross I is equal to minus k. And then, as I said before, j cross j is equal to 0. All right, so if you don't remember this stuff from Math Modelling 1 and or Physical Modelling 1, then you'll need to go back and revise that. Or, you know, there's multitudes of YouTube videos on how to do cross products. All right, so having done that and doing our maths, we get minus 460 times k. I said before that the cross product takes care of whether it's a positive or negative moment. So we don't have to, you know, to look at each thing in turn. Right? We can just allow the if we do the cross products properly to tell us whether it comes out to be positive or negative. So here we've got 4/5. So this is the x component of the force, horizontal, positive, and the y component, which is the distance that we calculated when we did principle of moments, right, dy positive. So we've got positive times positive, but because we've got j cross I, it's not k, but minus k. So that's how the vector moment equation takes care of the signs for us. Right? And we can see in our solution here, we get a negative 460k. Right. So what this k indicates is that the moment that we've calculated is a vector, and its direction is along the z-axis and in the minus direction on the z-axis. So if we remember our right-hand rule, so if we rotate our fingers around in the direction the moment's going, whether it be clockwise or anti-clockwise, that will tell us the direction of the moment. Okay, so our thumb points in the direction of the vector. Right? So if we go that way, let's go this way. If we go like this, then our thumb is pointing in the direction of that moment. If we come this way, then the moment is back this way. So if we're looking at the XY axis from the positive z-axis, we're looking down here, we can see that a clockwise moment, so if we're looking down this way, we've got a clockwise moment around here. It's in the negative z or minus k direction. So that's why when I said before that if you have x to the right and y upwards like this, then to be strictly correct, anti-clockwise is the positive direction for a moment. All right, so that's the end of that problem. That was a fairly long explanation, hopefully not too long, but hopefully helpful. All right, so that's it. Thanks for hanging around to the end. If you like my videos that go through these problems in some detail and explain why things are the way they are and why we do things the way we do things, rather than just quickly giving you an answer, please give the video a like and maybe even subscribe. Not for my benefit. I don't get any money out of doing this, but as you probably know, the YouTube algorithm looks at clicks, and you know, if you think this might be useful for other people, then that will help the YouTube algorithm to suggest it to other people. All right, bye for now. See you next time.